the integral test. In the previous section, we learned about a technique called the test for divergence. In this section and in several following sections, we're going to learn about various tests that can be used to determine if a series is convergent or divergent. The first of these new tests is called the integral test, and as the name indicates, it involves an integral. Suppose f is a continuous, positive, decreasing function on 1 to infinity, and let a sub n be equal to the function evaluated at n. Then the series from n equals 1 to infinity of a sub n is convergent if and only if the improper integral from 1 to infinity of f of x dx is convergent. So again, what does this mean? If the integral from 1 to infinity of f of x dx is convergent, then the corresponding series from 1 to infinity of a sub n converges. Likewise, if the integral from 1 to infinity of f of x dx diverges, so does its corresponding series. This does not tell us, if it converges, this does not tell us the sum of the series, just that the series converges. Use the integral test to determine whether the series is convergent or divergent. So here we have sigma from 1 to infinity of 1 over n to the fifth. And so if we were to consider, let's consider f of x equals 1 over x to the fifth, and we will note that it is positive, decreasing, and continuous. So, if this converges, then so does the corresponding integral. So let's evaluate the integral from 1 to infinity of 1 over x to the fifth dx. Alright, so remember this improper integral. To evaluate it, we rewrite this as a limit with t approaching infinity of the integral from 1 to t of 1 over x to the fifth dx, which would be the limit as t approaches infinity of negative 1/4 x to the negative fourth from 1 to t. So that would be the limit as t approaches infinity. And we can actually, let's see, we'd have a negative 1/4 t to the negative fourth minus negative 1/4 by 1 to the negative fourth. Now, as t approaches infinity, t to the negative fourth, remember that's 1 over t to the fourth, as t approaches infinity, t to the negative fourth will approach 0. So, applying the limit, we would have negative 1/4 times 0 plus 1/4, and 1 to the negative fourth is 1, and so that would be 0 plus 1/4, which is 1/4. Alright, so since the integral from 1 to infinity of 1 over x to the fifth dx converges, then sigma n equals 1 to infinity of 1 over n to the fifth also converges. Again, that does not mean that the sum is 1/4. It only means that it converges. Let's see another example. use the integral test to determine whether the series is convergent or divergent. And we have sigma n equals 1 to infinity of 2 over n root n plus 3 over n to the fifth. And I can write this as sigma n equals 1 to infinity of 2 over n root n plus sigma n equals 1 to infinity of 3 over n to the fifth. And now this integral, this series is 3 times sigma n equals 1 to infinity of 1 over n to the fifth. And so this, since it's just 3 times something that converges, we know that this converges. From the previous exercise, we just did sigma 1 over n to the fifth. It converges. So then 3 times a convergent number, it'll converge as well. So we're going to focus only on this first term, sigma n equals 1 to infinity of 2 over n root n. We should note that this is a continuous function. I should say that if we were to consider the corresponding function f of x equals 2 over x root x, we could say that this is continuous. We can say that it's positive. Especially, we're concerned about x, for x greater than or equal to 1. It's certainly positive. Is it decreasing? It is decreasing. If you just sort of look at this, notice that if x, remember x, we're only considering x to be, in a sense, integers here. As x becomes larger, notice that the denominator becomes larger, and a larger denominator means a smaller fraction. So it is a decreasing function. We could be more specific by using the derivative and the first derivative test, but that's a good enough argument for me. Alright, so let's apply the integral test. Let's see, what is the integral from 1 to infinity? And I'm just going to go ahead and go straight to the limit definition for this improper integral. So limit t approaching infinity, integral 1 to t of 2 over x root x, that's the same as x to the 3/2 dx. Alright, I can bring the 2 outside, the integral and the limit, so that's 2 times the limit, t approaching infinity, integral 1 to t, and I can write this as x to the negative 3/2 dx. So increase the exponent by 1, multiply or divide by the new exponent, 2 limit t approaching infinity, and we would have 2x to the negative 1/2. I should say negative 2 x to, this would be x to the negative 1/2 over negative 1/2. Evaluated from 1 to t. Let me bring that negative 1/2 out. Remember, dividing by negative 1/2 is the same as multiplying by a negative 2. So this becomes then negative 4 limit t approaching infinity, x to the negative 1/2 from 1 to t. So that's negative 4 limit t approaching infinity, x to the negative 1/2, that would be 1 over the square root of t minus 1 over the square root of 1. As t approaches infinity, the square root of t approaches infinity, and so then this fraction, this 1 over the square root of t, will approach 0 as t approaches infinity. So then I would have negative 4, and applying the limit, I'd have 0 minus 1, and so then it approaches 4. Again, we already knew that the second term converged from our previous exercise. So by the integral test, sigma n equals 1 to infinity of 2 over n root n plus 3 over n to the fifth converges. Use the integral test to determine whether the series is convergent or divergent. Sigma 1 to infinity of 1 over n squared plus 6n plus 13. Well, again, if we sort of consider the function 1 over x squared plus 6x plus 13, let's consider a couple of things. Is it continuous from 1 to infinity, right? We're only concerned about from 1 to infinity. So we might check to say, well, are there any zeros in the denominator? Checking the discriminant, 6 squared minus 4 by 1 by 13 is, what, 36 minus 52? That's less than 0. So there are no real zeros for the denominator. So it's continuous. All the terms are positive, so it's certainly positive. Is it decreasing? Well, if x is greater than or equal to 1, x squared and 6x will both be increasing, so the denominator will be getting larger, and so then the fraction will be getting smaller. So yes, it is decreasing. All right, so we've met all those we've met all the necessary requirements to use the integral test. So let's apply the integral test. So I need to integrate from 1 to t, and again I'll just go straight to the limit form. So limit as t approaches infinity, integral from 1 to infinity of 1 over t, from 1 to t, integral from 1 to t of 1 over x squared plus 6x plus 13. All right, and we've seen how to deal with an integral like this back in our unit on all the integration techniques. And what we do is we complete the square in the denominator. So let's see, that's x squared plus 6x plus 9. All right, and so if we add 9, we have to subtract 9. And so then this becomes limit t approaching infinity, integral 1 to t, and I'd have 1 over x plus 3 squared plus 4. And I recognize this integrand as dealing with that arctangent, right? And so this ends up being limit t approaching infinity of arctangent of x plus 3, and I forgot the 1. We need a 1/2, right? Because this is a square, that's a 2 square. So limit as t approaches infinity of 1/2 arctangent x plus 3 over 2, and evaluate that from 1 to t. We can bring that 1/2 outside, so I've got 1/2 limit t approaching infinity. And let's see, I'd have arctangent of t plus 3 over 2 minus arctangent of 1 plus 3 over 2. Now, as t approaches infinity, t plus 3 over 2, that will approach infinity, and the arctangent as we move further and further to the right, the arctangent approaches pi over 2. So we'd now have then 1/2 of pi over 2 minus the arctangent of 1 plus 3 is 4 over 2 is 2. Arctangent of 2. And so that ends up being, well, the arctangent of 2 is some real number. And so this is a real number. And so therefore, by the integral test, sigma n equals 1 to infinity of 1 over n squared plus 6n plus 13 converges. All right, let's see another example. Use the integral test to determine whether the series is convergent or divergent. And we have our old friend, sigma n equals 1 to infinity of 1 over n, the harmonic series. And we already should know the answer to this. We should know that this diverges using the argument that we showed in the previous section. But let's see a different kind of argument. Let's apply the integral test and see what it says. All right, and so if we consider f of x to be 1 over x, for x is greater than or equal to 1, all right, for on 1 to infinity, well, it's certainly continuous on 1 to infinity. It's certainly positive, and we know it's decreasing. So we can go straight to the integral test. So limit t approaching infinity of the integral from 1 to t of 1 over x dx. That would become the limit t approaching infinity of the natural log of x. I should put an absolute there, but we won't worry about that here. From 1 to t. And so then that would be the limit t approaching infinity of natural log t minus natural log 1. As t approaches infinity, the natural log of t approaches infinity. Natural log of 1 is 0, and so this limit approaches infinity. So by the integral test, sigma n equals 1 to infinity of 1 over n diverges. And again, we already knew that. We're just showing another example on how we could use the integral test to show that something diverges. So now we're going to consider a special case, sort of an important case. For what values of p will this series converge? And we're considering the series from 1 to infinity of 1 over n to the p. And we're going to break this up into several different cases. All right, so the first case. What if p is less than 0? If p is less than 0, then the limit as n approaches infinity of 1 over n to the p, well, remember that if p is less than 0, right, if p is less than 0, then, in a sense, we have one, if we remember that this means the same thing as n to the negative p. Remember, p is less than 0, so n to the negative p, but p is negative. In a sense, we have n to a positive number. And so n to a positive number, and remember, n, as n approaches infinity, you would have infinity to a positive number, and so this would be an infinite value. And so since the limit of the terms is not 0, this is divergent. All right, so if p is negative, diverges. What if p is equal to 0? Well, then the limit as n approaches infinity of 1 over n to the p would be the limit as n approaches infinity of 1 over 1, which is the limit as n approaches infinity of 1, which is 1, which is not 0. And so this also diverges. Now, what if p is greater than 0? Well, then we have a couple of different cases. If p is greater than 0, we're going to split that up into a couple cases. If p is greater than 0, let's first consider p equal to 1. If p equals 1, then this becomes sigma n equals 1 to infinity of 1 over n, which diverges. All right, that's the harmonic series. However, what if p is not equal to 1? So if p is not equal to 1, let's apply the integral test. And so then the integral test, let's apply the limit. Limit with t approaching infinity of the integral from 1 to t of 1 over x to the p dx. So that's the same as x to the negative p. And so then that would be the limit with t approaching infinity. And I would have x to the negative p plus 1 over negative p plus 1 evaluated from 1 to t. Now I can take that negative p plus 1, that's just a factor. I can bring that outside. So, and I'll write that as 1 over 1 minus p, limit t approaching infinity, and I'll make the substitutions. We would have x to the negative t plus 1 minus x to the 0, which is 1. All right, so now we just have to focus on that x to the negative p. Oh, and it shouldn't be an x anymore. I'm sorry, I made the substitution incorrectly. That should read t to the negative p plus 1. Sorry about that. T to the negative p plus 1. All right, so that's the same as... Now, let's look at this. T to the negative p plus 1, that's equivalent to t to the opposite of p minus 1. And so I can rewrite this as 1 over 1 minus p times the limit as t approaches infinity of 1 over t to the p minus 1 minus 1. All right, so now at this point, we have to sort of break this up into two further cases. Our first subcase will be if p is between 0 and 1. If p is between 0 and 1, and let's just focus on this limit, then our limit as t approaches infinity of 1 over t to the p minus 1 subtract 1. Let's focus on this. If p is between 0 and 1, then p minus 1 will end up being a negative number. So then you have t to a negative number in the denominator, which is the same as t to a positive number in the numerator. And so as we let t approach infinity, this term, that whole term will go to infinity. And so then this limit approaches infinity, and so diverges. All right, our last subcase. If p is greater than 1, then the limit as t approaches infinity of 1 over t to the p minus 1 minus 1. And let's again look at this. If p is greater than 1, then p minus 1 is a positive number. And as t approaches infinity, this would become a 1 over infinity minus 1, which is a real number. Right? It ends up being negative 1, and so it converges. So, after all that, what is our conclusion? All right, so a conclusion. Sigma n equals 1 to infinity of 1 over n to the p converges for p greater than 1. This is an important series. This is called a p series. All right, so the p series converges for p greater than 1 and diverges for all other values of p. All right, that concludes the presentation for this section.